Good morning. Welcome to Krishna's classroom. What we do next is the well-known Baire category. I have already put the statement on the board, and we look at this, and then we look at the proof of this theorem, and the statement says the following. Suppose Xt is a complete metric space. Then let Un be a sequence of open dense subsets of X. Then intersection Un is known. Okay. That is, if you take a countable collection of open dense subsets in X, then their intersection is non-empty. In fact, we prove a much more stronger result to show that intersection Un is dense. So that's what we prove. Now an equivalent statement is in terms of closed sets. Let Fn be a countable collection of non-empty closed subsets of X. So they are non-empty closed subsets of X such that X is the union of Fn. Then at least one of the Fn's has a non-empty interior. Now, another way of putting this across is this: a complete metric space cannot be a countable union of lower dense closed subsets. Okay. No complete metric space can be expressed as a countable union of lower dense closed subsets. As you have seen, if you take once you take Rn is complete. Now you take any proper subspace of Rn, which is a closed subspace and is lower dense. Now you cannot express Rn as a countable union of lower dense closed subsets. Now this is the theorem, and that's an example. Now, first before we prove this result, we would just ask why it is called a category. Okay, because sometimes Baire's category theorem simply called a category theorem, or it's a Baire's theorem, or Baire's category. How this category comes into the name of the theorem. So let us look at the following. Okay, so the question that we asked is, remark, theorem is also called category. So we ask how this terminology came in. Why it is called a category. Now there is a classification of sets in metric spaces as sets of first category and second category. I will just define this and then express this or rewrite this theorem in terms of the statement of first category or second category. So let us write this. So any countable, now you see, we call a closure interior. Now this we have already proved. Now any countable, so first category. First category sets. Any countable union of lower dense sets is called a set of first category. Now all other sets are called sets of second category. All other sets are called so we have this classification, sets of first category and sets of second category. And the base category theorem talks is regarding the sets of first category. Or it says no complete metric space is of the first category. So the Bayes theorem no complete metric space is of or in other words, all complete metric spaces are of second category. Now, one of the corollaries of the Bayes category theorem is this, or I'll come to that later. But before that, we prove this theorem. Okay, let's give the proof of this theorem. Now, what do we want to prove? Okay, first we make a statement or the relation between the first statement and the second statement. Okay. Now, we now give the proof of the theorem. The first and the first statement is equivalent to the it shall indicate the proof. Now, first we prove this so that we need to prove only one of the statements. Okay. So, we shall prove this. Now, the equivalence of these two statements follows from the fact that if G is open and everywhere dense, then its complement is closed and nowhere. We call that G contained in X is open and dense G contained in X is open and dense if and only if F which is equal to that is the complement of G in X denoted by F is closed and lower limits. We use this fact. Now apply this. You take the statement, one of the statements, and look at what it means for the complement. Okay. Hence, looking at complement of first statement, one gets the second. And vice versa. That means if you take union UN and take the complement of that, then the complement is essentially intersection over an UN complement. Now UN complement is to be taken as Fn, and then go for the interpretations. Okay. So what we do is, so that's how you prove the equivalent. So we prove the first statement now, and okay, this means that union in use this. We now prove in fact a stronger version of it. That is, we show that intersection over n un is not only non-empty, but is dense under the given conditions. So let us prove this. So what we claim is this. So what are the assumptions? The assumptions are each un is an open dense subset of X. Open dense subset of then intersection. What we claim is this intersection over n of this non-empty. And therefore it is also non-empty. Needless. Now let us prove. So let now we show that that's it. Now how do we prove this? You are given the set X, this is X, and U is a subset of it. It's not as I have drawn here. What we want, what we assert is that if X is an arbitrary we show that for every R positive BXR, the open neighborhood BXR with center at X and radius R intersects Q. That is no. This is what we do. This is true for every R positive. So this is the statement that we are going to. Okay. So how do we start? Let us start working on this. Okay. So let us start working. So U equal to intersection each UN is open and dense. Now, these are the basic assumptions. Let us use this. So note the following. Okay. So we have U1 is dense, which implies for every R positive, VXR so we have started with an arbitrary element of X. VXR intersection U1 is not. That's the first step. Therefore, what do we have? What is the implication of this? Since this is non-empty, there exists some element x1 which is in VXR as well as in U1. Now that implies there exists an R1 positive with 0 less than R1 less than R. That's the condition on R1 such that B this is actually the closed ball of radius R1 with center at x1. It's something like this. See, you have an x here. Now you have a suppose x is here. You have an intersection here. Now what you have is this is one. Okay, take U1. Now what you do is take x belonging to x. What happens? Now you take any R or any R, take it VXR. Now you see that this VXR intersection VXR intersection U1 is not empty. That's what I said. U1 is not empty. So there exists an x2 here, x1 here, and a R1 such that the closed ball of radius R1 the center at x1 is contained in this is what you get. Okay, where bxr less than or equal to r. So when you put a square bracket, it means you are talking about closed form. Okay. Now let us take u2. Now u2 and x1 belongs to x. Therefore, what one gets is this: u2 intersection is not a. You are repeating the argument, okay, which implies there exists x2 belonging to E R intersection u2 okay, R1 intersection such that, what more you can say. So you see, you are using the density of u2 now. Okay. So this is non-empty and you have an x2 and further where x is R2 positive such that one by 2 square, that is 1 by 4, such that B dx2r2 is contained in u2 intersection B u2. Now U3 is dense index, which implies U3 intersection not empty, which implies there exists R3 positive with 0 less than R3 less than 1 by 2 cube, etc. So this kind of argument you can continue. Now you have got, so R1, so you started with X, then you have X1, X2, X3 and so on, and repeat the argument. Repeat the argument successively. To obtain a sequence, n belonging to n, such that Pxn Rn such that Xn belonging to X and 0 less than Rn 1 by 2 to the power n, such that E is contained in this is what you end up with for every n, and so on. Thus what do we get? Thus we obtain a sequence such that Xn is contained in Px. This is a collection of Now we claim Xn is quotient. Now you look at the way in which Xn has been constructed, and you have got the Rn having this particular property. So we have for m less than or equal to n, e less than or equal to e plus xn. Now this is less than or equal to sigma k equal to m to n 1 by 2 to the power k. And what we observe is that sigma 1 by 2 to the power n is a convergent series. It's a convergent series, therefore, which implies the sequence xn which means that you can make this arbitrarily small by choosing n and m sufficiently large. Okay, so given an epsilon, there exists a number capital N such that for all n and m greater than n, this inequality is less than epsilon. So this is a Cauchy sequence. Now, now X is complete. That's assumption, which implies the sequence xn converges to some x naught belonging to x. That is infinity. Now note that is closed because it's a closed ball with radius rk and center at xk. Therefore, this implies x naught belongs to E rk, which is contained in E minus 1 intersection k. And that in turn implies x naught belongs to intersection intersection. What does it mean? This means that tensile x so that's the way in which you prove it. Okay, you start with a ball of radius r centered around the point r whose intersection with u1 is non-empty because u1 is dense. Now there is an element x1 chosen from that intersection. Once again you can construct a radius r1 with r1 chosen as 1 by less than 2 and such that the ball is inside that region and so on, and continue the process. Now intersect with u2, intersect with u3 and so on, and repeat this kind of argument. You get a sequence, and that sequence is a Cauchy sequence, and therefore since x is complete, you get the whole sequence converging to an x0, and x0 has a property that x0 is xr intersection u, because x0 is in bxr intersection uk for every k. That's why this is true. Okay? That shows u is tensile. Now this is the proof of the theorem. So the Baire category theorem has also can be stated as follows. As no complete metric space is first category. Now you see that if you drop this completeness, then it is not true. Why it is not true? Okay, so I make a remark. Plenty of examples for this. This statement. So you take this See, consider Q is atom. Now you can write there are countable number of elements, countably many say infinite. Now you can take each UN. Now UN is and you have we have Q equal to 1 to infinity or I'll put it this way. Let me write here FL. And Q can be written as the union of, that is, each Fn is closed and over X. Okay, so I think I'll stop today's talk. Thank you very much.